Hi, everybody. Sorry I'm a bit late. And I hope I have you turned on. I'm going to turn this up. Okay. I had to move from my usual spot at my desk because I've got some construction happening at the house. It's going to be going on for the rest of the semester, unfortunately. And it's like right out my window, so I couldn't stay there. And you can probably hear it now even. So I think I'll just stay as far away as I can instead. Okay, so this week, okay, so things that are happening. I'm gonna share my screen with the iLearn page so everyone's on the same page, huh? Okay, so we're doing minerals this week. We're starting rocks and minerals. We're gonna start with the minerals, then proceed to the rocks. There is no new lab this week because I want to give you time to work on your exams. That's the other important thing to know. The exam is open. It is less than 40 questions. I think there are 30-ish are multiple choice true false matching. And the remainder, I think maybe 8 are short answer of some kind. I think technically they're called essay questions on iLearn. So it just gives you space to write. The questions ask, I've given you a different diagram in each question, and I ask you questions about it that I want you to answer in that space. So I've given you plenty of space to write, so don't worry about that. Are there any questions about the exam while we're talking about it?
Yeah, you said that there are short answer questions, right?
Yep.
Are they like do they have to be like long like two paragraphs, or is it like
Oh God, no. No. Nothing like that. In fact, some of them are really short, like words, a few words would suffice. I think that's true.
okay.
No. This is not long. Like the longest answer might be a very short paragraph. So a few sentences, 3 or 4 would do the trick. So it's nothing extensive. It literally has more to do with, do you know what you were doing when you did your labs? Did you understand what you were doing? And can you do that again? So I said studying your labs and studying the keys is important. I'll emphasize that again. It's important. That's basically what the short answer section is about.
Okay. Thank you.
Sure. Any other questions? Okay, so maybe something will come up and we can talk about that later, certainly. All right, so the study guide is there. If you certainly don't want to start until you're ready to take the whole thing, until you have, I've given you 2 hours officially. I don't think you'll need even an hour. I expect that some of you are going to race through this. I don't advise that, by the way, but I expect that some of you will end up racing through it in maybe 15 or 20 minutes. But if you took your time and read through all your options on the multiple choice true false matching, thought about your answers, and gave yourself time to be thorough with the short answers. That's the thing, is like with the short answers, don't be too short, right? Like if you know more stuff about what I'm asking about, give it to me. Tell me what you know. That's the whole point of the exam, is for me not to guess what you know. Because I've had, students come to me after exams. Well, I know that. Okay, well, show me. You have to write it down. I don't know what's in your head, right? So you have to give me the details like you're answering one of the lab questions, that kind of detail. Don't just say, yes, this thing is one of those things and it does this. Give an example. Tell me where that happens on Earth. You know, I'm just trying to give you an example. It's not a very good one, but that's the idea, is explain yourself. So give me more info. Okay, I'm saying too much about that, but that's open until, I gave you until Monday next week at noon to take this. That way, if you work during the week, but you've got the weekends free, you have time, or vice versa, hopefully you'll find a moment to take the exam. I saw that nobody had tried it yet, so you're not like jumping for that. I assume that now that you're given some time for the class with not having a lab this week, I expect that for some of you, that will be divided between finishing up the labs that still haven't been submitted. Please submit them if you've got them. Just even if they're like a few days late now, get them in, because I haven't graded 5A, 5B, or 6. That's, you know, all the Google Earth stuff and the earthquake lab. The virtual earthquake lab should not take very long. And I see that a few people that normally turn their labs in haven't turned their labs in yet. So don't hesitate, just jump on that and you'll knock it out pretty quickly. But also, you know, at the same time, read the whole lab, understand what you're doing, because you're gonna see a question about that on the exam, you bet. Okay. So this folder right now, all it has in it is some links. I'm gonna show you a page that we're going to use that is the best thing I've seen out there that we can use as like to learn rocks and minerals in a virtual environment without having our hands on all of them. And I remember to bring your kits. I pulled mine out. They're a really nice specimen. So I'm really pleased about how they turned out. I'm going to use some of these as examples today. I hadn't really thought that closely about it, but I will do that. And if I forget, please ask me to show you examples, because I'm going to talk about some of these in today's slides. Okay, so that's what we'll use when we do start the lab. We're going to go to this site. So that's all I put there. Okay. Don't forget, I just put it up. I kind of forgot about the quiz to go along with the minerals. That is up now. Oh, I think it's less than 30 questions. It might be like 28 or something. We can go find out right now. No, it does not say without me going into it, and I don't want to try that right now. Okay. So any questions about anything? Questions about the labs that you're struggling to finish or anything like that? If it's a long, complicated answer, I might ask you to wait until noon and talk after I'm finished going over slides, but otherwise hit me.
There is a question in the chat.
Oh, can you please tell me what it is? My window's, again, not big enough really to have all it open.
It says, can we submit a lab after we completed the exam?
Why would you want to do that? Because I just said that the exam is going to contain questions, detailed questions about things that you did on your labs. So I really don't advise that. I advise you to do the lab, you know, even if it's like the easy questions only and you save the hard ones until later. Okay, so yes, I said, okay, I said no originally. I said no, that I wouldn't take labs that prepared you for this exam after the exam. But if you have a good reason, let me know, and then turn it in, and you can turn it in and send me an email separately and just let me know like why you couldn't get it done on time. But I really advise you to finish them and then take the exam. Okay, I won't lecture you guys about that. And I really like with lab 5, I'd like some feedback on that now that like at least 15 of you have done that lab now. Did that take a long time for you to do? For the people who didn't struggle with the technology, like uploading the geologic map of California, the topo maps and all the KMZ files with the earthquake data and all that. If you didn't struggle with the technology, did that lab take you more than a couple hours?
It took me a few hours. But I mean, I didn't find it particularly challenging. I already know how to use Google Earth. One of the main things though that made it take longer is I kept having this glitch where when like on the final question, yeah, it won't show
right, the
underwater.
topography was doing that. You're right.
Yeah,
right.
yeah. And so I kept having to try over and over again. And so that made it take longer just because it wasn't displaying the underwater
I recall
topography. But then eventually I was able to get that fixed. It fixed itself. And
yeah,
so
it
then
was
I was
weird
able to
because
just smooth sailing. But it
yeah,
wasn't a hard lab. It's just technical difficulties with Google Earth glitching, not showing underwater
okay.
topography was the only thing that I struggled with
That
personally.
was a hassle. Okay.
Yeah.
Anybody else have the same problem or a different problem with the technology?
I had a similar problem. Sometimes the layers wouldn't pop up like they were saying.
Oh, really? I
Yeah,
didn't
like
see that
I had
happen.
issues with I think it was the magnitude one. Like I tried, you know how it told us to switch between the different magnitudes? When I
Yeah.
would try to specify which one I wanted, it would start glitching. So I'd have to like restart the whole thing over.
Oh, that's a
Yeah.
bummer. Okay.
Yeah. But that's
Okay.
it. Other than that.
Okay. Thank you. Okay. So, can you guys, I don't know, if you want to use the chat, maybe that's the best way to do it. I'll open it if I can find it. Please let me know in the chat. Sorry, I'm looking at blah, blah, blah. I'm trying to find the chat myself. Okay, in the chat box, let me know like total estimate how long it took you to do lab 5, 5A and 5B. So the intro where you like learned how to use Google Earth if you didn't know already, and then then using it with the tectonic data, plate tectonic data. A total of 3 hours, 3 to 4 hours. Do you think that that is reasonable for this class, given that was sort of over 2 weeks? And it was like, okay.
I think it's reasonable and understanding, but I think just loaded with everyone else's coursework, it can sometimes be like, it
That
just
one
happens
felt
to
like
be
too
that
much.
like these long labs get paired up with other assignments that are long from other classes. So it's just like, feels overwhelming sometimes.
Yeah, I got you. I realized that. I was feeling that for you, for sure. That's why I made sure that the virtual earthquake lab was really short. So I hope that you were happy to see that too, and that you were watching a video for that one as well. So I'm going to try to mix it up a little bit more. Plate tectonics and seismology, like earthquake stuff, there's so much there, and so much of what we'll talk about with like other landforms relies on the tectonics and relies on understanding earthquakes a little bit and being able to talk about different kinds of faults and folds and basins and hills and, that kind of terminology. So those are really the big ones. And I hope that going forward, they'll be shorter. And I will try to do that and not try to like do a 5A, 5B, that was to make sure you could use Google Earth, right? And now that you have used it, I hope to use it more. I hope that you don't have the same technical issues, of course. But if we run into if there are problems with the layers, for example, we can always like cut out parts of labs that are causing trouble. If you guys let me know what's going on. Okay, so thanks for that feedback. I appreciate that. Like I said, no lab this week, so you can breathe easy a little bit, the exam instead, of course. But if you've done the other labs, you should be ready. So that's a good thing. Okay. Unless there are any final comments, I'm gonna go find the slides for today. We get to talk about minerals, which is pretty exciting to me. When I started grad school, I actually wasn't going to be a metamorphic petrologist. That's what I'm gonna stop this. That was my training as a PhD student. Kind of you get in geology or in earth sciences, you get kind of labeled as being a specialist depending on what you did. Sorry, I can't do two things at once. I'm trying to stop the share and why won't it go? Where's the button? Sorry, it always tucks itself away up here. There it is. Oh, how annoying. Okay. So I got to grad school and I thought I was going to be a structural geologist, which means I've mentioned structural geology before, which means that I would study faults, faulting, that process. In fact, the project was meant to be out in the basin and range, and I was supposed to be using a radiometric dating technique called apatite fission track dating. So apatite is a mineral, and fission tracks. I showed you an example in one lecture that are damage trails from the fission process, the radioactive decay process. In those minerals. And so you can use that to actually get an age for a mineral and therefore a rock. And that one happens to be, it's more like a thermochronometer. So temperature, age dating method, instead of a geologic event like crystallization of a magma or metamorphism. Thermochronology dates the last time rocks may have undergone faulting because it exhumed a block that cooled rapidly, or it could be a shear zone in the middle crust that are now exhumed. It could be, in this case, in the basin and range, it was to look at the literal basin and range structure. So to look at those normal faults that drop down the basins and raise up the ranges. And they also bring up, we use the word exhume, like, exhuming bodies out of, yeah, that's gross. But anyway, we use the word exhume to structurally, meaning along faults, bring rocks up to a higher level. And so you can exhume these really hot, they're high temperature, relatively high pressure rocks from the middle and lower crust that get brought to the surface. And so we can study these different structures that do that. And that was going to be my job, my task for my PhD. But then after I applied and got into Stanford, I got a phone call it was like Saturday morning or something. I got a call from Louis Liu, who ended up he was kind of like buddies with my PhD advisor, Gary Ernst. I think Louis was one of Gary's first students, and they were at UCLA together for a long time. And then Gary came to Stanford to be a dean, and Louis came along with him. Anyway, Taiwanese geologist called me up, and it was really hard to understand him, and especially on the phone when you can't like read somebody's lips. I don't know about you, but I find it harder to listen to accents on the telephone than in person. Anyway, he was talking about ultra high pressure metamorphism. I knew what metamorphism was, and I'd studied it as a major and everything. But I certainly didn't know what ultra high pressure metamorphism was. And I was going to study these rocks that maybe had micro diamonds in them, and this mineral called coesite, which is just a high pressure variety of quartz kind of. But I didn't know that. Even during this conversation, I didn't know that. And he invited me to go to the Ural Mountains, which divides Europe from Asia. Basically, it's east of Moscow, maybe 500 kilometers. Anyway, it rises up. You've seen that little like weird hook shape in the Arctic that's kind of in Russia, up in the Arctic. That's Nova Zemlya. That's at the top of the Ural Mountains. So that's kind of where they are. It goes from the Caspian Sea to Nova Zemlya. Anyway, I was working down the southern part, not all the way in the Caspian Sea, but we started it was my first ever trip out of the country too. Gary literally sent me to Siberia, literally, because I flew from San Francisco. There was a stopover in Frankfurt, but we couldn't get off in the northern Urals, and then finally in Novosibirsk in Siberia. We picked up a couple of Russian, like big time Russian geologists that worked at the academy there, Russian Academy of Sciences. So they were important higher up guys. They were coming to meet, not us, our advisors. Anyway, we went through Kazakhstan and then ended up in the Urals there. Why am I telling this story now? I've kind of forgotten. Why?
I think it's cool.
I was starting to say like why, like how I got to study minerals and rocks, because that's what we're starting to talk about now. So the chance to travel is the reason that I became a metamorphic petrologist, believe it or not. Anyway, so I studied these high pressure, relatively low temperature rocks that were part of the continent. This was a continent-continent collision, kind of like the Himalaya, Tibet, but with no plateau, just the mountains. Anyway, they are not spectacular mountains at all. They are flat. And we had to go down into a river gorge that had cut down through the plain to get to the rocks because it was so flat. And so I learned those minerals, like some pretty ones. Garnet, you don't have any, a lot of ones you don't have. You'll see them in the online lab though. Garnet you may have run across though, just because it's a semi-precious gem. They're nice red rounded crystals. They're dodecahedrons. They have 12 sides. Do is 2, deca 10. So dodeca is 12 sided, because you needed to know that. Right. And some really pretty green pyroxenes. You will see some pyroxene at some point. Some muscovite mica. You do have muscovite, although it was slightly different chemistry. I'm not going to be able to get it out of here. If you've got your kits, you can go ahead and pull them out and just check them out as I go through. It's number 7. It's the flat silvery one. This is a great example of having just one plane that it cleaves along, it breaks along naturally. So there's the bonding that holds the layers of these micas together is relatively weak compared to the bonds within the layer. And so they break into these thin sheets In fact, Muscovite, I think was named, what I've learned is was named for Moscow, because they used Muscovite in their windows, like thin sheets of Muscovite as windows in the olden days. I don't know when. Anyhow.
So the name of the glass is actually called Muscovite glass.
Oh,
So that's what they were. That's what they referred to the Muscovite like windows that they would make. They called it Muscovite glass.
I need to look into that. I'm gonna totally, because I need to.
I'm pretty sure. I think that's what I've read. Muscovite's actually one of my favorite minerals.
Cool. Hey, I'm into that. I'm wearing my favorite one. It's kyanite. It's blue, and it forms in these long, it's called bladed, like a knife blade. It's long and wide, but thin. It's got a lot of color. I like it. But muscovite is a very fine mineral, and it's really common. So you will see it in real life, accidentally bump into some, even at the beach, like in the sand grains. This forms a tiny little shiny sand grains. Anyway, I expanded my knowledge of minerals when I had to start teaching mineralogy. I wasn't hired originally to teach mineralogy at San Francisco State. I was brought in to teach petrology, and mostly just igneous and metamorphic rocks, because sedimentary rocks and minerals I don't really know that much about. Yeah, a little bit, because they come from the rocks that I work on, but I don't know much about the clays and all that. Anyway, but I ended up teaching it because the one person who was teaching it decided to stop teaching it. So I stepped in and did it. Anyway, I had to relearn how to identify minerals down an optical microscope. It's called a polarizing microscope. And so that was another steep learning curve, and to learn a bunch of new minerals actually that are more common in igneous rocks. Now my research has expanded to include igneous rocks as well. So, and what's nice about igneous rocks is they have a pretty simple mineralogy, and like 10 minerals. And if you know those 10, like you're good to go. Metamorphic rocks are like a whole different story and more complicated. That's why we'll start with igneous rocks next week. Okay, so slides, enough chatting. The other reason I'm allowing myself to chat is that I know, oh wait, wrong, sorry, that's the wrong one. That's the one I borrowed slides from. The lecture is not hugely long. We'll finish in plenty of time this week. In fact, what I plan on doing is, here, let me get this switched over. Let me share this. What I plan on doing is to get you oriented to the mineral website that I was showing you, the one that has kind of virtual mineral testing. So you have some, I'm going to talk about some of these properties today. So this is totally on task. Your kits came with some supplies, and then you should have received at least a week ago, I hope, for those of you who are in California. I hope you got your boxes with the HCl, the dropper bottle with HCl, a magnet, a glass plate, and some safety instructions. I am going to give more, I will explain the safety instructions as we go, but just leave it capped for now, and I'll explain before you need to use it on your minerals. So it comes with a streak plate. This is just a piece of ceramic. Usually they're not quite so cute and tiny. The ones, the typical ones we've got in lab are maybe 3 times this big, but it doesn't matter, because you can actually just wash them, clean them off, and they're good as new. So if you run out of space, if you run out of space because you have too many streak marks, you can clean them and start over. This is meant to, it's a hardness test, because this ceramic has a certain hardness to it that is based on how the molecules are bonded together. And the mineral has a certain hardness to it. And so one way you can find out is to actually scratch the mineral across. Here, I'll do it a bunch of times so you can see. You scratch the mineral. I can't see myself. I think I'm holding that in focus. You scratch it on the streak plate and it gives you a certain color. Like I would say that that's either gray or black. Sometimes they say black. I say black. A black streak. So that's powdered mineral. So the ceramic plate is harder than this mineral because I was able to powder this mineral into it. So that's one piece of information. And the color of the streak is also another piece of information. This color of the streak is different from the color of the actual mineral. Like it's two different answers. You'll be surprised in some cases what the streak color comes out as based on what the mineral looks like. You'll run across a few that will puzzle you. Okay. So, and it comes with one of these lenses. So I'm probably just going to use my hand lens. I mean, this is a Geologist hand lens, looks like this. And you wear them around your neck because if you just put them in your pocket, you leave them on the rocks and you lose them forever. So you wear them on your neck. And in this case, you take your mineral specimen or your rock specimen and you hold it very close to your eye and inspect the mineral or rock really close up. These guys, let's see, that's not bad actually. You can see quite a lot. No, that's better than I expected actually. Yeah, you'll be able to see the details that you need to see for sure. So that's good news. You also got, there was one other thing that you got in the rock kits, and now I don't have the rock kit with me because I had to move my desk. But it was another piece of testing. Maybe it was a nail. That's probably what it was. Okay. That's also for hardness because the steel nail has a certain hardness. Okay, so minerals. This is tourmaline that you're seeing on the screen. That's pretty, I like tourmaline a lot, especially as an undergrad. I think I might have called it my favorite mineral at the time. This is watermelon tourmaline because it's green and pink like a watermelon. They have a lot of watermelon. Tourmaline comes out of San Diego locally, if you're a mineral hunter at all. Okay, I have to move the participants because so I'm not going to be able to see you guys at all. I'll just be talking to my screen. Don't all log out and leave me talking here to myself. Okay, so chapter 3, this outlines what chapter 3 goes over. It is, it goes into more detail on different, like on the non-silicate minerals than I do here. And it gives you a little bit more information about the bonding and the periodic table of the elements than I'm going to in lecture. But that's good because in some cases, I expect the text to back me up like that. So instead of me giving you a chemistry lecture, I'll just talk to you about more directly about the minerals. So here, what I'm going to start off, and as does your chapter, I'm going to define mineral for you and then give you a little quiz to see if you guys can decide whether certain substances are minerals or not. I'll talk about the common minerals in the continental crust and the oceanic crust. I'm going to talk about a little bit about the silica tetrahedron. So it's this like pyramid shaped molecule that is important in silicate minerals because that's the silicate part of the silicate minerals. And silicate minerals are most of the vast majority of the minerals in the continental crust, even in the oceanic crust, in the crust. Okay, I'm going to go into a little bit about the crystallographic structure of different silicate minerals so that you understand that they go into different groups based on sort of what properties they have. And minerals in the same group tend to share physical properties. So like physically testing the hardness or the streak, those are physical tests. Or optical identifications when you look down the microscope and you try to identify it that way. I will go over non-silicate minerals a little bit, and then we will talk about the physical properties of minerals that you're actually going to use in your lab. Okay, so this is an important one and will definitely be a quiz question at some point. Definition of a mineral, it is and you don't have to quote this, you just need to get all the elements right. It's naturally occurring. That's important. It cannot be man-made. It is inorganic, no organic material. Okay, so nothing that was from a living thing. And so no plants, no animals, no trees, and nothing like that. It has, it's a compound that has an orderly internal structure. So it doesn't have to be a perfect crystal structure, meaning there are no errors in its structure. And that happens a lot. And it even has a predictable chemical composition. So those two things are different. One is an orderly internal structure, meaning crystalline. So there are bonds that you can, we can sketch out the bonds in that piece of mica to show the little weak bonds in between the layers and stronger bonds in the plane of those sheets. They have a characteristic chemical composition. That doesn't mean it's not variable or that certain trace elements, meaning trace element, there's major elements, there's trace, and then maybe rare, you go with that. Trace means it's like less than 1%. It's in there in very small quantities. So trace elements might be a straight, like we know that the chemical formula for quartz is, and I think you must have a piece of quartz in here. I can't test it, so I'm not sure exactly, but I bet you that's quartz. Number 5, you can look at the identification table and tell me if I'm wrong. I also don't have my glasses on, but oftentimes it doesn't form those nice prisms that you might be thinking of, but it's just like an opaque or semi-translucent white, or it might even be colored mineral. It comes in lots of different colors: yellow, purple, pink. What other colors have I seen? I've seen lots of inclusions, like black inclusions, and then there are trace elements that cause those color changes. And there are common substitutions, like aluminum happens to have a very similar ionic size, that the ionic radius of an aluminum ion is similar to silicon, the Si part of the SiO2, and it has the same charge of +2, and it has other, like the bonding characteristics are similar to the silicon as well. So aluminum can substitute in for the silicon in quartz. So if I were to do a chemical analysis of this, I might see that there's a tiny bit of aluminum in there too. That doesn't mean it's not quartz and that it's not a mineral. What the definition is saying is that I can predict the chemistry of the quartz. It's mostly SiO2. 2 silicons and one silicon and 2 oxygens. Okay. It also has a certain crystal form. So the crystal form, like for quartz, for example, might have those prisms. Do I have an example of? I have some little ones, some colored quartz. It's citrine. It's a yellow one. I don't know exactly which trace element does this, but do you see the little prisms at the top there? Oftentimes you'll see long ones that sell individually in stores, or little clusters. So you might even have some of your own. But this is the crystal form. It grows like this commonly when it's got a void that it can grow into. So oftentimes people go and get those, I think they're called thunder eggs or something like that. They're these spherical nuggets they extract out of volcanic terrains. And oftentimes those are like bubble voids or some other kind of void inside into which these crystals grow really nicely and with the beautiful crystal form because it's unimpeded with, it's not competing for any space in there. And so you crack them open or you cut them open and you might get agate, which is just like, imagine these, well, that's the side of this, isn't it? If you took a slice of that, you'd see that this looks like the agate. So it's striped because it's got different chemistry, different contaminants you might think of as it's growing from the edge inward. So it might continue to grow. If fluids are flowing through the fractures in the rocks, and this is well after it's crystallized, fluids flowing through, pick up some silica, crystallized quartz, and it might fill up eventually. Okay.
I have a fairly large piece of quartz with some nice crystals on it if you want me to show the class so they can have a good example of large quartz crystals.
Go for it. Let me just make sure you're set up. Try. I think you can. Oh, nice. Yeah, that's exactly what I was talking about. Those are beautiful. Right. So quartz, when we get to cleavage, it doesn't break like this. This is how it grows naturally. So yeah, those are great. Thanks, Kay.
Yeah.
Okay, so let me go back to slides. Okay, so that is the form. And a mineral also has a certain set of physical properties so that you can test it and get the same answer over and over again. So it's repeatable, you know, it follows sort of the scientific method, and you develop a scheme whereby you can identify different minerals using some of their physical properties. Not all minerals, like you're not going to be able to identify all minerals just by looking at a small piece of them. No way. Even with the physical properties, oftentimes you need the optical properties in addition because you can't see everything with your naked eye, or even with, you know, with a small bit. This is considered with a naked eye. Even with a little bit of magnification, you can't see. And then if you can't see something with the optical microscope, that's when you go to an electron microscope. You've seen images of like flies' eyes magnified with the little pits and all the little hairs and all the legs and all that. That's from a scanning electron microscope. Those can see a lot of detail at a very small, you know, very small things can be magnified greatly. That's what I'm trying to say. Okay, so definition of a mineral. Oh, what's on the next one? Okay, so we're gonna do a little quiz. Yeah, we can make it a little bit bigger. We're gonna one by one, and let's see. I think the best way to do this is for you guys to shout out answers maybe, or no, oh, I know. The participants window will work. You guys can use thumbs up, thumbs down to vote yes or no. Or there's a yes, no button. Okay, that's more direct. Okay, so please vote for all of these. Using these rules, is petroleum a mineral? I'm missing something. I should have added a word. Let me just add one word while you're voting. Okay, now you can continue voting. Don't let my addition of a word affect your vote. I see some no's. I see all no's. So does anyone want to volunteer why you think petroleum is not a mineral? Go for it, Kay.
It's organic.
Oh,
It came
that's true
from-
too. Yes, it doesn't.
Yeah,
Well,
it has an
and also
organic origin.
it's also not solid.
Yeah, it's liquid and it has an organic origin.
Totally. Okay, how about coal? Coal is solid. You guys still think no? Do you know how coal forms? Do you know how petroleum and coal form? So petroleum, it starts off being, they probably form pretty close and similar environments, actually, swampy environments where there's a lot of organic material that's accumulated in certain areas. Coal would be sort of, there are different grades of coal. A poor grade coal that's not any good for burning for fuel is what it might start out with, that organic material. Like imagine just swampy leaves and roots and tree bits and all of that stuff getting accumulated at the bottom of the swamp, and then more sediments on top, and then over time you've got this really thick organic layer. At the beginning, when it just starts to heat up, it starts to undergo changes, all that stuff. You're gonna start to crystallize minerals out of it eventually when the temperatures get high enough, after it gets buried deeply enough. So, excuse the cat. That's a first. The organic matter starts to break down. Listen, where am I? Coal. Okay, so minerals start to crystallize. Coal is when it's like thoroughly crystalline. That's when it's like the best grade of coal that's good for heating. Petroleum, it can only get to a certain temperature once it heats up too much, it turns to natural gas and you've lost the actual liquid petroleum. That starts off similarly. It's organic matter that is broken down. In this case, it's liquid that actually fills pore space in between. Like you can imagine sand in a big pile of sand, and you can fit a lot of water into a cup of sand because of the pore space. That's where the petroleum is. Anyway, that's what that stuff is. So it's all organic. Thank you. How about obsidian? Do you guys know what obsidian is? It's that black. Oh, do you have some? You might have. I think you have it in your rock box. I'm sure you have it in your rock box. It's black glass that comes from. It starts off as rhyolite, so really felsic lava. Essentially, it's a glass flow is what they come from, or an obsidian flow. It quenches quickly, but it's also a very dry, very low water content. It doesn't have a lot of things that would become gases in them. So anyhow, what about obsidian? Volcanic glass. I see one yes. I see 4 no's. Others of you aren't going to vote? 2 yeses, actually. Come on. It's 50-50. Chances are pretty good. Okay. I'm going to point to one thing. Orderly internal structure. What that says, even though it's a solid, even though it's naturally occurring, it's not crystalline, it's glass. Glass is an unordered solid. So there's no internal crystal structure. So that's a no. How about amber? You guys know what amber is? Amber is like fossilized. Is it fossilized? No, it's not fossilized. It hasn't been replaced by rock. It is fossilized, or I almost said it again. It is, let's say, ancient tree sap that is preserved. Often you've seen these probably. Oh, wait, didn't you read an article about a feather preserved in amber? No, that wasn't an amber, was it? You see bugs trapped in amber. It's like a golden color. It's formerly tree sap. Sorry, was there a question?
Like in Jurassic Park with the mosquito.
Right. In Jurassic Park, if you've seen that one. Yeah, exactly. How about amber? Do you think amber, are these the same votes? Okay, wait. I don't know if these are the same votes or not. I'm going to clear you all. I want fresh votes for amber, please. Someone think about which part of the definition of mineral you're going to point to disprove or to prove your case. Does anyone want to volunteer why they think amber is not a mineral? Anyone? No?
I guess amber is organic.
It's organic. Yes, absolutely. Thank you. Yes, it is organic. How about opal? Opal is not organic. Let me tell you how opal forms. There are mines in Australia that are famous for opal. It is a silica. I can't say, I have to be careful of the words I use. It is made of silica. It has structural water in it. It is not quartz. It doesn't, it's a naturally occurring substance. It's not organic. But the water in it. A second cat. That's Bo. Apparently you're going to meet the cats at this desk. There are 4, by the way, and you'll probably only ever see 3 because one's so fat she's not hopping up here. No way. Okay, opal. I'll help you with this one. No, because that structural water that's in it, it's not completely crystalline. So opal is also another word. We say opal A, opal CT. I think there's some other opal variants. Anytime you've got like chert, we've been talking about chert in the Marin Headlands, those red beds that are all folded. That's the siliceous ooze from the radiolarian bugs at the ocean, at the seafloor, the sediment there. So that is silica also, but it's not quartz. It's not crystalline completely. It's partly crystalline. So opal is not, because it's only partly crystalline, similar to the chert. Okay. And opal, like I was saying, opal A, opal CT, those are different kinds of grades of how crystalline the mineral is. Okay, pearls. I want to go a little bit faster now. Pearls, how about votes for pearls? I'm seeing some votes change. I'm not going to clear it. You change your vote if you want. What about pearls, do we think? We think that's organic, don't we? Are you guys thinking the same thing? I'm going to volunteer that one for you. It's made by an animal, so it's organic. It fails that part. How about salt? Salt that comes out of your salt shaker. How is that formed? Does anyone know? I mentioned that the Morton Salt Company had some salt ponds in the South Bay for a long time. And I know that somebody else, I don't think it's Morton, has salt ponds in the East Bay still down there.
Can I chime in on the formation?
Go for it.
So salt, sodium chloride, it has like a cubic structure.
Yep.
Right? And it's formed largely in beds where there were like ancient oceans and it evaporated, right? There
Totally.
evaporates.
Yeah, totally. Evaporites. Yeah, exactly. You need an evaporate environment like a desert, someplace where there's water only temporarily, like you're saying, like water comes down, it absorbs whatever salts are in the soils, and because it gets very, again, the water is very salty because it only gets rain once in a while, or it's a bed that never drains and it evaporates, leaving behind the salts. Yes. So it could be shallow seas, it could be salty lakes, it could be any of those things. Good. Okay. How about synthetic diamond? There's diamond and there's synthetic diamond. I kind of made that complicated. Okay. Synthetic diamond. Does anyone want to chime in? Look at the definition. Again, a solid, naturally occurring inorganic element. Naturally occurring. So if it's synthetic, is it natural?
Can I chime in?
Yeah, go for it.
I don't think it is a mineral because, as you said, it has to be naturally occurring, and since synthetic diamond is not naturally occurring, that's why it's not a mineral.
Right, totally. Good job, thank you. Okay, how about you call them vitamins and minerals? How about that bottle of vitamins at home that you've got? Maybe. Are those minerals? No, you guys are just, I think you're just leaving your answers alone. Those are man-made, number one. So no. And mineral is used in a very different way when they talk about vitamins and minerals, right? Okay. How about granite, the rock granite that we've been talking about? And I just kind of gave it away, but what do you guys think? Now, I know that you guys, at least I'm going to say most of you are going to say this, are going to make this mistake. You have one box of minerals that you got for your lab, and you have one box of rocks. But I bet you're going to refer to both of them as boxes of rocks, but you would be wrong. One box really is minerals. What's the difference?
Can I volunteer? Sorry, I know I talk all the time.
It's okay with me.
Okay. So rocks and minerals are different because rocks are typically a collection of multiple minerals. It's not a single element or compound that has a specific crystalline structure.
Right.
And so rocks have like a whole bunch of different minerals in it. Like I know granite has quartz in it, but it has like other minerals, I think like feldspars and stuff, right?
Yeah, totally. Yeah, anytime you see those pink crystals in a granite, you're definitely looking at a feldspar, but they're also white feldspars that look kind of similar to the quartz, which is more grayish. But yeah, granite has multiple minerals in it. And so it's a rock. It's not a mineral. The minerals are the individual minerals. Like granite is made with biotite. This Muscovite piece is driving me crazy. I'm going to have to find it a new home, or I'm going to end up breaking it trying to get it out. Muscovite, biotite, quartz. So there, we need some feldspar too to make granite. Where's the feldspar? Not that. Oh, that's feldspar. It's kind of tannish, pinkish. So there's granite. Is there another feldspar in here? maybe not, or that might, no, I don't think so. It might just be the one feldspar. So the pinkish feldspar, the whitish quartz, those, that's a pretty good granite right there. It's just the proportions that change the name. So sometimes we'll say like it's a granodiorite instead of granite. And there's a rock called diorite too that is darker than granite. And so it's more intermediate composition than granite is felsic. Remember I said felsic, intermediate, mafic compositions. So that's because it has a lot less quartz than a granodiorite has a lot less quartz than a granite does. And it also has more of a plagioclase feldspar instead of a potassium feldspar like this pink one. So those are some differences. Okay. How about that? Well, how about water? Is water a mineral? Last two here. I didn't clear you, so sorry. You got to change your votes.
Can I chime in?
Yes, please.
Water is not a mineral because
It's got a regular chemical composition. It's H2O, right?
yeah, but doesn't a mineral I thought it was because it was not solid, so I thought that.
Yeah, that's it. I know I'm messing with you.
Okay.
Yeah, it's not solid, but ice is ice a mineral? Do you want to take that one too?
Yeah, I think ice is a mineral because that one is solid and is naturally occurring as well because we can get it like in a refrigerator and like freezers as well.
Well, is the ice that we make in our fridge a mineral compared to ice like in a glacier? There's a
Probably.
difference, right?
Yeah.
So what about the ice in your fridge? Is that technically a mineral?
I'm still gonna go with yeah on that one.
I think no, because it's man-made, honestly. I'm going to say no, even though natural processes like physics and chemistry and all that create the ice, we put the water in there to make it. So I'm going to say no. I veto that decision, but ice is that forms on your windshield overnight in the winter, or that's in the snow that you ski on, or on the glacier that you climb on, you see from a distance. That's definitely a mineral. Okay, good job. I hope you had fun with that. Okay, so we're gonna learn some mineral names, and we already started learning some. Slowly you'll get them. Okay, I'm trying to find the ideal window size here to share this. Maybe you can't even see that. Okay, the common minerals in Earth's crust, and right now we're talking about all of the crust. So I believe I'm pretty sure they're lumping in the oceanic crust with the continental crust here. Yeah, totally, because that's too much pyroxene and amphibole. Yeah, totally they are. Okay, so this is common minerals in Earth's crust. Look what makes up the most. 39% is plagioclase. This is a kind of feldspar. Feldspar, I think it comes from the German meaning field rock, spar stone, I think more like field stone, feldspar. That's where it came from. Anyway, plagioclase is more it has calcium and sodium largely. It's really common in both mafic, felsic, and intermediate rocks, but it's the only feldspar that's in the mafic rocks. And the more you get toward a more mafic composition, the more plagioclase there is, the more calcium there is. But if you're talking about a granite, then it's more sodium plagioclase. So it's variable. It's what's called a solid solution of calcium and sodium. well, never mind. We'll get to that. So it's a solid solution, meaning the calcium and the sodium. Remember I was talking about the substitution of aluminum for silicon in any silicate mineral, or just quartz. Same thing happens here. The calcium and the sodium exchange for one another. They fit into each other's spaces in the crystal lattice. And they meet all those conditions. They're Goldschmidt's conditions for the substitution, elemental substitution like that. And the rules are based on like, is the charge the same? And you're like allowed plus or minus 1 charge difference. Is the ionic radius similar? So it needs to be within like 15% of the usual, like if it's aluminum substituting for silicon, aluminum has to be within 15% of the size of the silicon in order to fit, number one, but in order to make a good substitution. And then it has to have a similar bonding characteristic. So you might know that metals have different kinds of bonds, metallic bonds compared to covalent bonds compared to ionic bonds. Ionic bonds are easy to break, like sodium from chloride that you break all the time when you dissolve salt into water. Covalent bonds are a lot stronger. Okay. So that kind of difference, the more similarities there are, the easier the substitution. Okay, so there's a solid solution there. What else do we have? We have alkali feldspars. Okay, so these have more potassium in them than the plagioclase feldspars. These can either have sodium, potassium, and aluminum. Plagioclase, they both have aluminum. Okay, so, and then quartz is mostly silicon and oxygen, except for a rare substitution. Pyroxenes these are chain silicates. So remember, I was talking about the sheet minerals, like I'll hold up the biotite because it might be easier to see. This is biotite. It's also a mica, just like the muscovite is a mica. These two are sheet silicates. It's given another name, kind like phyllosilicates or phyllosilicates, spelled just like phyllo dough, you know, that dough that comes in like Greek pastries or just pastries where there's lots of little flaky layers. That's what this is, phyllosilicates. But just remember sheets and that'll be good. So these minerals are in this group here, 5% micas. The feldspars, this is an alkali feldspar in your kit. That's one of these, your 12% alkali feldspars. Your quartz is here, 12% quartz. And then you don't have any clay minerals. You're getting close. You've got a talc, I think, there. What is that? I've got to get to know your kits better. So those are the silicate minerals, the clays. You can crystallize clays like in mudstones and all of that, but the feldspars also break down to form clays over time. So like a granite is breaking down with rain and wind and just weathering. You start to get fractures in the minerals and they start to transform over time, especially in like soils or a sedimentary environment like that. Okay, so this abundance is, you can see that in the different elemental abundances. So the top 10 most abundant elements in Earth's crust are these. So oxygen and silicon are right at the top. And that's because, well, it goes back and forth. The crust is mostly silicate minerals. That means they have an silicon and oxygen in some ratio that is bonding together the other cations with it. So that's like an anion, the silicate part. So it's I think it's usually a -4. And the silica tetrahedron that I'm going to point to in just a minute has a -2 charge, I think. Yeah. And it bonds with positively charged ions like calcium, sodium, potassium, magnesium, the things on the other side of the periodic table, if you so on your left-hand side. What else? So that's where a lot of that oxygen and silicon is it's bound within the crystals of the crust. Aluminum too is found in a lot of these minerals. It's in the amphiboles, in the pyroxenes, it's in the feldspars, it's in the clays, it's in other silicates. Iron is much smaller component, 4.7 or almost 5%. You know, if you were looking at just the oceanic crust, iron and magnesium would be a lot higher, but this is them together for the whole crust. So iron, calcium, magnesium sort of go together as far as finding those elements in mafic rocks together compared to felsic rocks, which have more aluminum, sodium, potassium in them. But those are them. So they're there in like 2 to 3%. Magnesium's not quite 2%. Hydrogen, less than 1%. Titanium is a pretty common mineral, pretty common element in minerals, in common minerals even. There's titanium dioxide that you know from probably like sunscreens and stuff, that white paste, but that's also TiO2, titanium dioxide, is a mineral called rutile that's found in a lot of these mafic rocks. Anyway, I'm straying from the topic here. There's some numbers to back up what I'm going to say about the minerals found in the oceanic crust. Okay, so we've talked about basalt, right? The ocean floor is almost entirely basalt, except where, you know, we're sampling bits of the deeper part. The lower part of the oceanic crust has the plutonic variety of basalt called gabbro. So that's right here, basalt and gabbro. So this would be the lower part of the oceanic crust. It's plutonic, but still mafic. So, but we call it gabbro when it's plutonic. We call it basalt when the same composition, same chemical composition rock is volcanic. It's also half, so basalt and gabbro have half plagioclase. I mentioned plagioclase being like a calcium rich plagioclase that goes with mafic rocks. That's this. And half olivine and pyroxene. So olivine you might know because peridotite is a gem quality olivine. It's a green mineral. That and pyroxene is a black, very dark, almost like, sometimes it's like a dark blackish green color. A few pyroxenes are green. There's even one that's white, but color is definitely not a reliable way to identify minerals. Color will deceive you. So be careful. Don't just jump to conclusions when you see a particular color mineral. Not until you get good at identifying them. That you have to take my mineralogy and petrology class first. Okay, so the basalts that come out of the mid-ocean ridges and at mantle plumes that come up through the oceanic crust, that's where basalts are also erupting. So like Hawaii or Iceland. These are, both environments are from partial melting of mantle rocks. So peridotite is a name for a mantle rock. You can remember peridotite if you like, or you can just remember that it's the mantle rocks. I think right now that would be a fine way to describe it. But peridotite is a rock that it's mostly olivine. It's either that or a pyroxenite, which is mostly pyroxene, the other mineral listed here. So peridotite or pyroxenite, based on which one is more abundant. Okay, and the oceanic, oh, not the rust, it's the crust. The oceanic crust is somewhere between 7 and 10 kilometers thick, not at the rift zone though, it's thinner there, but certainly away from the mid-ocean ridge. Okay. Continental crust, there's a nice picture of granite here on the left. that is, you see I'm going to try to point, the pink alkali feldspar or the potassium feldspar. We usually abbreviate it and call this like K spar, because the K for the potassium and the spar for the feldspar. So that's usually K spar. So if I slip, that's what I'm saying, potassium feldspar. The white part, so where it's very bright white, that's a plagioclase, probably. It could also be another alkali feldspar, but oftentimes that's a plagioclase feldspar there. And that will be either calcium or sodium rich, more likely sodium because it's a granite. And then where it's like gray-ish, that's quartz. So because even though it's translucent, it's got other minerals behind it that we're seeing the light from also. So like there might be some dark minerals under that quartz grain right there to make it look darker gray. So so anyway, we got two plagioclase, or two kinds of feldspar, quartz, and the black minerals are either, this is quartz right there. That's a nice example of the dark gray, right there even. The black minerals are either biotite mica, the black mica, and I can't tell without getting a closer look. If you see like nice flat sheets with your magnifying lens, with something to magnify that, because you won't be able to see with just like holding it there like that. Or it could be an amphibole mineral called hornblende that I'll tell you about later. Oh, is that supposed to be an arrow there? It looks like there's an arrow. I'm not sure what it's pointing out. Okay, so continental crust is somewhere between 30 and 70 kilometers thick. That's a typical continent, like middle of the continent, or the old shield part, the oldest like cratonal areas where they dated like the center of Canada, the center of North America, from our Midwest up into Canada is the craton, so the oldest part of the continent. That dates back to beyond 4 billion years ago. It's a lot younger than the oceanic crust. Granitic rocks are pretty common, and we use that just to describe the continental crust overall. They're about a third quartz, a third plagioclase, and a third K-spar, with a smaller amount of the biotite and muscovite micas and this amphibole called hornblende. That's a black mineral. So we get granites during the process of subduction beneath a continent. So oceanic crust beneath the edge of a continent, where you get a typical subduction zone. Those initial basaltic melts that are partial melts of the mantle, those come up and they're passing through that 30 to 70 kilometer thick crust, and they're changing chemical composition as they go. They come out the other end oftentimes as andesite, which is intermediate in composition, or even felsic as a granite. Okay, so I'm describing a lot. You don't have to, we're not talking about memorization here, but I'm trying to give you an idea of the general differences in mineral makeup of the continent and ocean crust. Okay. Oh, I guess I should have waited until here. So subduction zone, here, the typical scenario, when it's an Andean type margin, so meaning an Andean type continental margin, where it's oceanic crust subducting beneath the continent. The partial melts that happen in the mantle, so that mantle peridotite or peroxenite or whatever it is, has water added to it from the subducting slab. It lowers the melting temperature, you get some basalts. The basalts enter, they're buoyant, so they're rising toward the surface. They pass through the continental crust, and they're taking pieces, incorporating those into the magma as it passes, probably melting some of that material, joined with other melts somewhere along the way. And with time, you're going to end up generating andesitic lava or andesitic ashes in that volcano. Oftentimes as ash because they're explosive type volcanoes. What was I going to say? Right. This would not be true in early Earth before the continents had already developed, because at first it was just like maybe volcanic arc underneath volcanic arc or oceanic plate beneath volcanic arc. And you're not going to end up getting granites out of that scenario. But once we had like well-developed continents, then yes, this process would work that way. Oh, and I've got the andesite down here. This is what one would look like. So this is a volcanic rock, right? It has a really different texture from a plutonic rock. We haven't done these terms yet, but we're gonna talk about them next week. So here we go. Plutonic rocks, your igneous rocks are of two kinds. Igneous means it comes from fire, so it's molten rock. They come from magmas originally, both volcanic rocks like lavas and ashes and anything that comes out the top of a volcano, and plutonic rocks that never reach the surface. They cool and crystallize beneath the surface. So when they cool and crystallize slowly like that underground, you get larger crystals growing compared to volcanic rocks where you got there's some crystals that you can see, these little black hornblends. This is a good place to see a hornblende. This is that amphibole I was talking about. So these crystallize, they're called phenocrysts. There are these little crystals that start to form early on in the magma chamber before the andesite was actually erupted. They just kind of hitchhike along the ride with the gray matrix part, the lava part, or the ash part that comes out when the eruption happens. It just brings these hornblends along. So its chemistry has less silica and more iron and magnesium and more calcium than a granite. But it's not mafic yet. It's still not a black or a dark gray rock. It's somewhere in between. There's a lot of plagioclase in there, even though you can't exactly see it. The hornblende is clearly there. It's got pyroxenes in there, so more black minerals, and even magnetite. Magnetite is, I think, 8 in your box, I think. It usually doesn't it's usually tiny little crystals in your rock. You don't get big hunks. But this is the kind of rock that you would get out of an explosive eruption like Mount St. Helens, or in the Mammoth area in Eastern California. There's an ash that was erupted about 700,000 years ago called the Bishop Tuff. There was an explosive, like huge Yellowstone type eruption that took place then in Eastern California that gave us like this huge pile of ash. And they actually, it's rhyolitic, but it forms columns. You may have seen like columnar basalts before. If you're driving through Oregon or Washington, maybe you've seen them, but oftentimes they're basaltic, but it happens in rhyolite too. Or if you've ever been to Devil's Postpile in Eastern California, that's near Mammoth. That's a columnar andesite even. So it can happen in whatever composition. The rhyolite is lighter colored. It has even higher silica than the andesite, less iron and magnesium than the andesite. And that's definitely has incorporated more continental crust. There's more quartz, there's sodium rich plagioclase, a potassium feldspar called sanidine that only ever occurs in volcanic rocks, biotite, and maybe some hornblende. So just a couple of black minerals, and that's it. Last couple of slides before I say goodbye, or before I take questions about your labs. I'll introduce the silicate subclasses. to do that, I gotta bring up the silica tetrahedron again. Now I say tetrahedron when there's just one, it's ON ending. When it's more than one, it's tetrahedra. So this refers to this structure, this pyramid shaped structure that is formed when you've got one silicon with a +4 charge paired or bound together with 4 oxygen anions. So these are forming a covalent bond. So they're strongly bonded together. It's these tetrahedra together that bond to the calcium, to the magnesium, to the sodium that's in the cation part of the mineral formulas. So if the silicon is +4 in the center of this molecule, and the oxygens are all -2 charge, that's -2, -4, -6, -8. This whole molecule together has a -4 charge. So that's an anion, that's a negative ion, negatively charged ion that can bond with those positively charged ions, cations, like the ones coming from the left side of your periodic table. I think I should be pulling up the periodic table. I think I'll start with that next week, or not next week, on Thursday. Okay, so we talked about like what defines a mineral. Some of these groupings that I'm talking about, though, these silicate subclasses, depend on the arrangement of the silica tetrahedra, how they're bonded together or whether they're bonded together. There's one group that has isolated silica tetrahedra, but the others form sheets of tetrahedra, like in the micas. There's a sheet of tetrahedra, and then a sheet of cations, and then another sheet of cations, and then maybe some hydroxyl groups, and then another sheet of silica tetrahedra. There are other minerals, those pyroxenes and the hornblende, they're black elongate minerals. We don't have good example here, but the hornblended pyroxenes, those are chains of tetrahedra. Okay, so all these minerals are crystalline, right? The atoms are arranged in a certain pattern, the crystallographic structure of the minerals. But the minerals themselves, when they're bonded together with the tetrahedra, they form different, a different arrangement. We're talking, yeah, it's the next slide. So the crystal is a regular geometric solid with smooth surfaces. So for example, this is some calcite that you've got some nice flat, shiny, they reflect light really well. Those are the surfaces that I'm talking about. These are the crystal faces that you see. And like in those pointy crystals that Kay shared with us with the quartz, those are the smooth surfaces that are called crystal faces. So the arrangement of these ions and the silica tetrahedron determine the shape of the crystal, the form of the crystal, the form that the crystal takes when it grows. I've said most minerals in the crust are silicates because they contain these silica tetrahedra that are bound together in different crystallographic arrangements. And I'm going to end on this slide for today. So there are 7. Ooh, am I missing one? I got to check that. I only see 6 here. There are 7 mineral subclasses. So that this is describing, sorry, 7 silicate mineral subclasses. That's important because they all are around the silica tetrahedra. There are ring silicates that are called cyclosilicates. We're just going to call them ring silicates because that's what the tetrahedra are bound together like. There are isolated silicate minerals. Some form a single chain. Some form a double chain. These are the hornblendes. These are the pyroxenes. The micas form sheets. So this is like the sheet arrangement. and some form a three-dimensional network. This is not a good example. The diagram is not doing its job really, but they form a 3D network. You can think of like a building block or something. That's like quartz and feldspars. So I'm going to give you some examples of these different minerals so that you can kind of get introduced to a bunch of different minerals. And then you're going to see a bunch that in your lab next week where you're going to test the minerals, the actual physical properties yourself. And you're also going to do it virtually online on that website that I showed you. But I'm going to stop talking there. I'm going to take any questions, and then I'm going to stick around as usual until 12:30. I can work with anybody on your labs if you've got questions. Okay, so any questions?
No, thank you.
All right. Well, you might change your mind. Otherwise, I'll see you Thursday.
Mary, could you keep it on this slide for a moment? I'm still writing down a little more information.
Oh yeah, sure, you bet.
Thank you.
Mhm. Oops. Something's happening.
Okay, thank you.
You're welcome. Oh, the sneakers. I would not have guessed that. Really?
Hello, can you hear me?
I can.
Oh, okay.
Hi.
Good. I just wanted to let you know that for the lab 2, the key, I was trying to like work it out because I didn't do so well on it. It's coming up as the transcript. I don't know.
Oh no, I'm sorry.
No worry.
Let me go fix that. You said for lab 2,
Yeah, the topographic map.
and that was the key, topo
Yeah.
key. I thought there was a problem with that and that I fixed it, but I will go back. Have you, just to check, you refresh the page just to make sure that you?
Yes, I just did it right now before class.
Okay.
I'll do it again right now just in case.
Okay. Because I will fix that right now.
Thank you.
You're welcome. Let's get rid of that. Come on. There it is. That's correct. Okay. Easy. Okay, that's fixed. Let me see.
Yes, got it. Thank you so much.
Good. You're welcome.
I still have a question about like labs.
Okay, which one?
I'm still working on 5D. I know I'm like a little bit behind because I finally got my job to cut down my work days. Sorry about that. Sorry.
Hey, don't apologize. Do what you can do.
I finally got them to cut down my days, and then as I said earlier, I got getting still all my other coursework done, but I'm still working at 5D, and then I still got 6 to do.
Okay. 6 will be quick, I think, for you, for everybody.
Okay. But is it okay if I pull up
Yeah, you bet. Go ahead.
5B?
Mhm.
Okay.
Okay.
So for these ones right here, I don't know if you wanted me to like sketch them out, like print them out, like sketch them, or did you like?
You can sketch them, or you can just insert the profile that you got. So when you do an elevation profile to answer those questions, let me just look at the lab. Doesn't that tell you to do that? It says mid-ocean ridge, thanks. Zoom in enough to see the ridge is a topographic high. It also has a rift valley running along. In the space below, complete the topographic profile of the Atlantic floor between. Okay, so you can approach this a couple different ways. I think since you have Google Earth, you know how to use it now, that you should go ahead and use it and follow the instructions and do a profile, one of the elevation profiles like you did across Mount Hood. Do that for these questions and then paste them in there, and then you can just like draw on those instead of sketching the whole thing out by hand. But if you want to, you can sketch the whole thing out. You just need to make sure that you include all the features. So you're probably going to want to do the elevation profile anyway, so that you answer the question completely.
Okay, but
It's
what
saying, go
but
ahead.
what exactly am I putting in there? Is it like the is it like the line that we draw, and then like sorry, like the line, and then like all like the elevations like that are in the oceans. Sorry.
Yes, right. So in this case, you're going to draw it from the coast of South America. You want to get on the continent there. It doesn't have to be the whole continent, but grab a little bit of South America on one end of your line and draw it all the way to the edge, the western edge of Africa. And it'll go across the entire Atlantic Ocean, right? In the southern hemisphere between South America and Africa. And then you're going to get the elevation profile for that line, which you know how to do now, right?
Yeah.
Okay. And you should be able to see, and I think we have a fix if there's any problems that you run into now. What you should be able to see is the topography of the ocean floor and then up against the continents. And it's really exaggerated vertically. So you can see like, the mid-ocean ridge really looks like a mountain out there.
Oh, okay.
You see what I'm saying?
Yeah.
So I want you to include those details. So you can go ahead and just like take a screenshot or grab that, put it in here, and then you can draw on that instead of sketching what you're looking at.
Okay.
You think you can handle that?
Yeah.
Okay. So that's what I want. That's what you should do for all of these, making sure that you capture like all the features that it says to.
Trying to see if there is anything.
The very last question has been tripping people up.
Oh, the question 29.
Yeah.
I haven't gotten there just yet.
Right. No, I realize that you're not there yet, but when you get there, it's the same idea. Like, you can get this one says to actually sketch it and not to use an elevation profile, but start by getting the elevation profile all the way from the East Pacific rise in the Pacific Ocean across South America, across the Atlantic, and to Africa. And it says to do that at 10 degrees south about.
Okay, so we're basically just sketching what it is like in 2 and 3, but adding all those that we see, right?
You're adding in, it's like across 3 different plates and across at least 2 plate boundaries. So there's a lot of information there.
Okay.
But you're seeing all the ridges and all the trenches and all of that. That's the idea. And then you need to label all this stuff on it.
Is it okay if I show you my Google Earth real quick as well?
Uh-huh.
If it can
You have to stop sharing this one first,
appear.
and then you share the Google
Oh, yeah,
Earth.
here. Oh, sorry.
Sorry.
So I've added in like all the magnitudes and everything,
Uh-huh.
and plate boundaries.
Uh-huh.
Yeah. Stuff like question sorry. But like that's like the one for question 2. That's the path that I drew right here.
Okay. And you got an elevation profile, no problem. You want to show me the elevation profile?
Yeah. Huh. That doesn't seem right.
Okay, so you can fix this. So go do a right click on the same thing. So you can like close that and then right click on path 1 and it'll give you a bunch of options. I want you to go show me that.
Right here?
Okay, so go down to properties.
Properties?
Yeah. Is it being slow? This seems like it's slowed down your
Oh,
internet. Garnet, actually. Okay, so go to measurements, I think. Click on the measurements tab. Oh, that's not it. How about view? The view tab, that's the middle one.
Oh, view. Okay.
Sorry, not that one. Try altitude. That's the one. Okay, so click on that, clamp to ground, and choose relative to clamp to seafloor. Clamp to seafloor, not relative to seafloor.
Okay.
Okay, now
Press
say
okay?
okay. Uh-huh. And then go and try and do the elevation profile again.
So this is like what you want us to draw.
Yes, that's it. Yeah. So that's how you fix it if you get that error.
Okay. Okay.
Yes.
Just
What you're-
okay. Wanted to make sure,
Sorry, you broke up.
Sorry, I just wanted to make sure that this is what
Yes.
you wanted us to draw, right?
That's the idea. But like I said, except for the very last one, you can go ahead and plop this in there if you want, and then you can annotate that to explain your answers.
Oh, okay.
You know what I mean? Like draw arrows, like circle things, draw arrows, like write words to.
I'm sorry, you broke up a little bit. Oh yeah, yeah.
Okay.
Like include like by including like all
Yeah,
the volcanoes, plate names, and everything.
that idea. Yes. Yeah. Exactly.
Trying to think, is there anything else? Because I'm trying to get this like all correct. Oh yeah, just question number 9 real quick when it says in the vicinity of ridges and in the vicinity of trenches. I saw a couple trenches, like I noticed one over here.
Uh-oh, you froze. Oh, there you are.
Oh, I froze. So like here's like a trench right here, and then a ridge right here. So for when you were asking, are you asking for like the depth of like all these dots right here?
Oh, so you're gonna have to rephrase the question because you broke up enough. I'm not sure what you're asking.
Oh, okay.
You said this is question 9?
Yeah, question 9.
Okay, let me go read it myself.
It
Okay,
says,
the different colors of
look
episode.
closely at around the.
Yeah, yeah. So you're interpreting those epicenter dots, yeah.
Okay.
And then your legend is right there that you need to use to interpret those, both the magnitude and the depth. Right? Magnitude is the size of the circle and depth is the color. Right?
Okay. Just wanted to be sure. As so I checked a couple trenches. Like I saw like none of those like those dots like in the. I saw like none of those like those dots like in the like around the trenches, but I saw like a couple of the ridges, and you saw a few of those dots like around the ridges, like it's circling around them, as you saw.
Yeah. So I think what you're saying.
I just didn't know what to do.
What to do with which question? Oh, you mean the patterns?
I just didn't know how to do with the with this part 1500
It's
kilometers.
all, so are you talking about, what question are we talking about now?
Sorry, I know I'm all over the place. When it says scan right here for 1500 kilometers, right? We're talking about the dots that are centered around the both ridges and trenches, right?
Oh, down that box. Okay, wait. Okay, so on the left-hand side, you're describing the seismicity near the mid-ocean ridges. Okay, in general. Nothing that's named ridge necessarily, but just like out in the middle of the Atlantic or in the Eastern Pacific or even the Indian Ocean. Go look there. Then the trenches are, you found a trench here, right? So can you zoom out? Because I have no, Puerto Rico, I'm not sure exactly. Are you in the Caribbean?
Yes.
Okay. Right, okay. Okay, cool. That's one example. Not every, the pattern isn't as clear in all places. So like the pattern for the trenches there is it's not the most ideal example. You might go look in Japan or like Tonga. Those are really nice examples. The Aleutians or Kamchatka, northeastern Russia. Those are great examples where the seismicity makes a really clear pattern.
Okay.
Go look there because this is kind of messy. I want you to notice, for example, that the orange epicenters are closest to the trench. And that the purple or red, the blue, purple, red, the deepest ones are inland or far, they're beyond the volcanic arc even. It's like the middle ones, like green and blue, maybe green, blue, yellow are over the volcanoes. And then the purple, red are even farther away from the trench, beyond the volcanic arc even.
Okay.
That's the pattern you're going to see if you move over to the Western Pacific and get out of the Caribbean.
Okay. So move over more to like the Pacific Ocean more.
Yeah, to the western side of the Pacific. I mean, this doesn't tell you where to go, right? It just says like near one of some ridges or some trenches. So if
Okay.
from here, like if you want to look at a ridge, I would go look at the mid-Atlantic ridge. So all the way over, you have to get out of the Caribbean to see that. Yeah, I don't see it yet even. Okay, so there, out there in the middle with the red line going up and down.
Right here?
In the middle of the ocean.
Oh.
It looks like you're going towards the Pacific. I was talking about the Atlantic, but that's okay.
Right here, right?
That one. Okay, so there's a ridge right there. Yes. So that's what I'm talking about. And 1,500 kilometers on either side of that. So to the west or to the east. That's where you're gonna look. And
that would
that's
be
not very far. if you take the ruler and measure 1,500 kilometers, you know, it doesn't get you to the continent.
Okay.
So that rig,
Okay, now I
follow
totally
it
get what you're
around the
saying.
whole Earth, right?
Yeah, okay.
And all of the seismicity there, it's all shallow, isn't it?
Yeah.
So in that description, in that question, you want
So
to
just
talk about, describe the pattern that you see, right? It's kind of in a straight line, but it zigs and
Okay.
zags. And, you know, all of the dots, they're all lined up along the plate boundary. And they don't go very far off the edges. And they're pretty regular. Yeah. So just
Yeah.
use descriptive terms to describe that, and, you know, do something similar with the trenches. But with the trenches, you want to give some relationship to the volcanic arc too. Like, look where the trench is, look where the volcanic arc is, where's the edge of the continent, and then compare the seismicity like that.
Okay. Got it.
I hope that's clearer.
Yeah, it definitely is. Yeah.
Okay, good.
Mhm.
Okay, so I hope I saved you some time there, and you, if you can just pop in those elevation profiles, it should go quicker for you.
And I do believe that's it. Yeah, because everything else seems to be straightforward and
It's under control.
Yeah.
Cool. That's great.
okay. Sorry about that. If I wasn't as clear.
No problem. No problem at all. Just clarifying with you.
Okay.
Good luck on that.
Thank you.
Have a good day.
You too.
Bye.